Okay, so the camera is not working, so I'm sorry, you won't be able to see me in this one. So just voiceover slides here, but this is pretty quick. We're going into phase 3 of our kind of development life cycle here. So we just have a few things that we want to talk about. Anyway, I just want to bring this back up, just like I do kind of every time. We're in phase 3, but we're still kind of doing initial model building. Now, I should probably do a better job of this in class, but initial model building can really be a conceptual model inside your head. It doesn't actually have to mean, that you're developing a machine learning model, or it could be a very simple version of your model, just a correlation, or maybe just exploratory data analytics. So we did a lot of that kind of already. But really what we're talking about kind of in this last phase, like I said, is kind of in model creation, but still could be in this initial model phase. All right. So let's just jump into it. Just have a few things to cover. We've covered a bit of this in class, but parameters versus hyperparameters. All right. So remember, parameters, when we think about, the every data scientist's goal here, just to put things in this is just an ugly example, in a data frame, right? So we have our variables here, so on and so forth, yada yada yada, right? All right, so these are our parameters. Okay, these are gonna be the parameters. This is another word for this is just features, variables, however you want to say it. All right, the hyperparameters, okay, are going to be the things inside of the model that we can change. All right, so I've already shown you some examples of these, but K in KNN is a hyperparameter, right? So we can adjust the number of neighbors up and down. If you've watched that video already, you totally understand what I'm talking about. So we pass in our parameters and we adjust the hyperparameters. There are limitless numbers of these as we move into more machine learning. This is a very simple example, but essentially it's the things that we tune inside the algorithm. All right, we're going to talk about thresholding. We've talked about this a bit already, but just to be clear, right? All of our machine learning outputs give us results in percentages, all right? And the percentage is just on a distribution from 1, to 100, okay? So we can decide anywhere inside this distribution of 1 to 100 where we want. Say we just do it, say this is 20, right? And this is 80, right? So anything on this side of the line is going to be a 1. Anything on this side of the line is going to be a 0. All right? We decide, okay? The results of most machine learning models is just a distribution of percentages, all right? And then depending on where your threshold is set, it will classify, all right? It'll classify those numbers as either a 1 or 0. It defaults to 50, okay? So anything at 50% or above is going to be a 1, all right? Anything below is going to be a 0. But it does not mean that we can't change it, right? Is this the eraser? It appears to be. All right, it doesn't mean that we couldn't move this way up, and make it like 75%. And that would just depend on the type of question you're asking and how cautious you want to be. We'll get more into that. All right. All right. Feature engineering is probably a really under discussed topic in data science. I would say in almost all cases, developing better features will improve your model much more than changing the model. Let me say that again. Often the way that people approach machine learning is to try all sorts of different models and just see which one gives you the best results, okay? That is one way to go. A better approach is probably to build better features, better parameters, right? Better things to put in the model to make it understand the target better, right? This is always going to be an added benefit about how you do that. All right, that might mean that you have to go out and just gather more data. It might be that you have a bunch of text data and you need to convert that into some type of numeric representation, all right? It might be that you combine features together. It might be that you have a whole bunch of states and you collapse those into regions. there's lots of things you could do in the feature engineering space by combining or exploring different levels or doing clustering to create features that will enhance your model's performance. Okay, we'll see different examples of this. I'll try and work them in throughout the semester, but in a certain way, you're already kind of doing it, right? One hot encoding, you're creating different features, all right? So you're creating features, at least to the very least, you're giving the machine learning algorithm a better chance to understand the different layers of that particular factor. That is an example, all right? All right, last topic here, well, kind of last. So bias versus variance, again, a very large topic, but at its very, at the very highest level here, I just want you to make sure to understand that machine learning models require bias and variance to work. All right, they require a certain level of statistical bias in order for the models to work. If they didn't, they couldn't generalize. All right, so here when we look at this, all right, this example is an example of underfitting. All right, so here what we're doing is we're just drawing a line, and we're not accepting the fact that there's a clear arch here in this data, right? There's obviously an arch, right? So this would be an example of creating some type of linear fit, right? You do the typical regression, you just stick the line through the middle and hope for the best. All right, but most approaches in machine learning are not linear, right? They're usually non-linear approaches, non-parametric approaches where they can be flexible in terms of how they draw this dividing line, how they connect these dots together. All right, and this one is just underfit. Here, well, let's go out to this example, right? Let's go out here. All right, all the way out here. What is this? This is way overfit, all right? This is basically, you've just memorized the data, right? Just memorized it, all right? So imagine if there was just another X that was out here, right? How would this, what would the prediction be? This is pretty far away from that line, right? So this prediction would be pretty inaccurate, right? But we did the same thing here, right? Just notionally about the same distance. Because of this arc, right? It's gonna fit much better. It's gonna be closer. It's more accurate. Okay. So this is creating these local optimal lines, which always means that when you start to generalize it to larger data, it's just not going to work very well, right? Okay. So it's just memorizing the patterns that you have in it. You're way overfitting. Okay. And of course, what we see here is that we have, right? We have the optimal slope that clearly recognizes this simple kind of diminishing returns line here, right? With size and price being our two variables. Who knows what size is anyway? So that there's some level of diminishing returns, right? So you can better predict size and price if you just recognize the fact that it has this curve, okay? All right. So the idea is this is where we want to get to. I'll say this is an art, okay? If your model, there's been lots of good, PhD level, researchers that have created models that are just way overfit, right? They just dump everything in there. So we have to guard against that. And there's ways to be able to check. And usually data partitioning is a good one, right? If we know that we're memorizing our data, and then we go and use new data on the test data, what we probably will see is a pretty big drop in the evaluation. You can evaluate how the model is trained, and I'll get to that in a minute. You can evaluate how the tuning is affecting that model, and then you can finally see the test. One way to look at it is that if there is consistency across all three of those layers, you might be in that sweet spot. If there seems to be some inconsistencies to include suddenly big increases in performance, you might have a problem, all right? You might be in this overfit category. All right. So typically overfit means you're overperforming. All right. Underfit means you're underperforming. All right. So you can kind of look at it that way. This little target diagram is kind of helpful. I think it's low bias, low variance. All right. What this means is that, it's very tight in the middle. All right. So that's the bias part. And it's also just in the red. So that's the variance. All right. So we've hit the target in the middle, right? But we also probably wouldn't generalize very well if we had to predict like other data points kind of somewhere around here. It might not work very well. High variance, high bias, low variance. All right, so we still have our tight bundle here, right, which is our high bias. But again, we have low variance, which is the tight bundle, right? The high bias means that it's off the target, right? It's just not quite right. So its estimating error is going to be pretty high, all right? We still have a pretty low variance. Here we have high variance and low bias, right? So we're kind of in the middle, so that's good, right? We're in the middle, but that's good. But we've got a good amount of variance across the points. And then here, this is just the worst of both worlds, right? They still have kind of a tight general, we're in one general area, but we're way off the target, right? And it's still spread out a good bit. What we probably want, to be honest, right, is something here in the middle, right? Kind of in this sweet spot, right? And so anyway, I'm not gonna be able to draw it with much accuracy here, but what we would want if we look kind of over in this category here, right? This might be the closest thing. It might be that we would want all our dots to kind of be inside this white area, okay? So we'd still have kind of a low amount to medium bias, right? So maybe it's just right around this area here, but it wouldn't be so tight to where it would be myopic, right? It would just be too tight. We'd still have a good amount of spread, so that would be good, but generally still on the topic. So maybe a best model would be if everything was kind of in those first two circles, kind of in here, where we're generally right on the target, but it has enough bias and enough variance in it to be able to accommodate for unseen data, right? So remember, if we have this here, we have inject new data, it just won't generalize well, right? Because it just doesn't understand the patterns outside of this tiny little area here. Okay, so generally, I don't know if this is more confusing than not, but kind of what we're hoping for here is this, kind of sweet spot between all four of these categories. We're not in extremes in any one. So here, these are supposed to be just 4 examples of extreme scenarios in combination with low and high bias. But really what we want is just, we want it to be just right? We want it to be medium bias, medium variance. And that's the sweet spot, because that allows us to be able to accommodate for variations in the data, right? Allows us to generalize well, and it doesn't allow us to, create, large errors associated with what we're estimating these new data to be. All right. I'm going to stop here in just a minute, but last point here, I just want to make sure to emphasize this, is that evaluation is basically it's basically the entire machine learning process, all right? The more you're evaluating, the more you understand how your model is trained, the more you understand how it performs on unseen data, the more you understand how it performs on new information, the better you're going to be. All right. So, we have lots of situations here where we're doing evaluation, right? We're doing here, we're doing it up here. All right. We're doing it over here. We're doing it here and here. All right. This is model drift, kind of moved off a little bit, but all of these, and even, in large part, it's analytics, but you're kind of doing data drift analysis, right? You're still kind of evaluating if the data is changing. So a lot of this is just about how understanding the weaknesses of your model. The better you understand that, the better you'll be able to control for them, and the better you'll be able to return the value and answer the question that you're hoping to. The other thing, and we'll talk about this much later in the class, is it really guards against any type of potential, toxic outcomes associated with your models, right? And think about if humans are involved, right? If you understand the weaknesses and you've really done a robust job of evaluating how the model can work, what it can do and what it can't do, you've gone through the process of using your intuition to see if the data that you have matches the questions that you're trying to do. You go through all these processes, all these gates, you're going to do a much better job of potentially avoiding any devastating impacts that kind of machine learning can have, all right? Outside of maybe just normal business situations, but they've been used in situations that are affecting humans. So it's important to keep that in mind. The more robust we can be in evaluation and the better we can do the job up front here, making sure we got the question and the data, the better we'll be. All right, that's it. Another quick video. I will see everybody in class.